Okay. Hello, everybody. Good morning. I hope all of you are good. So, before starting, if you have any question about previous course or topics that we've had, soon we will be, during this week, I will announce you about the projects. That's what you need to do for machine learning project. And I want to let you know that if you have a specific project in your mind that you are doing that is related to machine learning, can be considered as project, but you need to discuss it with me. And you will have maximum 1 week to make decision and announce it on the Moodle. I will let you know so that if the project is acceptable or not, I will let you know. But there will be some options that you can choose, plus the project that you want to do specifically. There is no limitations that you only have to do what I want to say, but then you need to discuss it with me, see if it's acceptable or not. Any question? All right, good. So today we are going to talk about neural network and deep learning. So if you have had class with me already with reinforcement learning, we had to cover this area over there because we needed to use it in deep reinforcement learning. You've seen what we are talking about. But if you studied, some of you have specifically deep learning course, I know. If you have it, of course, you are more familiar with it. It will be not too hard to understand the concepts over here. But the most important point is that after studying whole linear regression and the topics that we've had, you will see how easy it is to understand today's course. Because now you will see that the same predictions, the same classifications, the similar concepts that we were talking about all are existing over here. And why we are talking about machine learning from basics, from the fundamental algorithms, is the same reason, so that we know all underlying understandings, all underlying equations, the cost function, everything we know, so that we can understand high-level algorithms easier. And afterward, you will see, okay, even if we study more complex algorithms, easier to understand. What's similar that happened in, for example, reinforcement learning course from last semester, if you have it. All right, let's dive in step by step. Today, we are going to quickly have a look at the linear classification, cost function, optimization, and most importantly, we are going to focus about the back-propagation algorithm. Then we talk about specifically about artificial neural network, and we talk about the deep learning and the basics of the deep learning, what we have there. So in addition to the books that I introduced for machine learning, there are two other books that can be useful from Bishop and Russell that you can study more about the neural network and deep learning over there. So if you want to remember about overview of the whole machine learning and what is the rule of the deep learning, we can say we had the artificial intelligence, then we had machine learning, that is subfield of AI. Then we discussed that we have supervised learning. We saw lots of different techniques for that. Then we saw unsupervised learning. We understand how it's working, and we saw practical algorithms for that. In separate course, we discussed about reinforcement learning, how it works. But now what we want to do, we want to focus on the deep learning. As you see, deep learning is in the center and has common with supervised, unsupervised, and reinforcement learning all together because it can be merged with all of those together. So it is clear that when deep learning is over there, then we can use it in supervised learning so that we have labeled data. We can use it in unsupervised learning that we don't have a labeled data. And we can use it in interactive mode as reinforcement learning that one agent is trying to interact with the environment. One additional point that we haven't discussed it, if we have time, we will discuss also some techniques over here that we have semi-supervised learning, that is something in middle of the supervised and unsupervised learning technique. So we say, okay, if we want to talk about the deep learning challenge, although neural networks are very old, but why there were a gap between progress with deep learning? So we had artificial neural network, and at some time, no progress anymore. For long, no progress anymore. Again, artificial neural network came up, and we end up with deep learning techniques. There are different reasons why there were gaps. One of the reasons with deep learning techniques, we need big data. In contrast to what we studied, the algorithms that we studied so far, with deep learning, we have large data. We need large data set to be able to train deep learning network. And the reason is that why nowadays it's easier, because we have better tools to collect data from internet. We have faster internet. We have lots of data sets, data on the net. Image, for example, we have the image net that you can take thousands of or even millions of labeled data images, for example, from ImageNet, that I will have a slide to explain it. Second reason that why we have deep learning neural network nowadays more under focus is the hardware. We have much more stronger hardware, the GPUs that you are playing games with them, or we have very advanced new GPUs like H100 processor, and that OpenAI is using that also, these kind of GPUs. They are useful for generative AI, large language models, and the recommender systems. So what is the GPU? This kind of GPU from NVIDIA is that like that. They have also built-in CPU and built-in structure that directly can connect to the network. Then you don't need the whole PC, that the bridge and everything flow from your system. Directly your graphic card can do much faster processing inside. So these are the new technologies of graphic cards that you can see even OpenAI is using for this new ChatGPT. I think older versions of this graphic card has been used over there. The third reason is the software. So we have big data, we have better hardware, better data, and also better software. Why better software? Because we have new models and new techniques, first of all. Second, we have new toolboxes and libraries that easy to use. You see that I'm teaching, like we are studying together 3 hours of one topic. Then with a few lines of code using libraries, we can implement it. That's easier and faster to bring everything to the code. And plus, we have pretty decent libraries over there. Like, for example, we have PyTorch, we have Kutenen, we have Keras, and many different, like TensorFlow. All these give you lots of programming functions to make everything faster, to develop your neural network, deep learning models, and more complicated networks that you want. In this course, I will focus during the slides that I am teaching to you. You will see some examples of the implementation. For example, how we can implement this part, 1-2 lines of code, and at the end we collect it all together. They are based on the PyTorch. Of course, you can use the TensorFlow or other ones, Keras, but we prefer PyTorch over here, and because it's a little bit easier and more compatible with Python. Plus, if you are using it with reinforcement learning, deep reinforcement learning, for example, IsaacGym supports these series of libraries. But if you know the concepts, doesn't matter. You can use all of them. But our preparation here is PyTorch. Any question? Okay. What was the linear regression? In linear regression, we learned that we have some data, and based on data, we want to predict the model. Simply, we want to find a line, intercept and slope that predicts this data for us. We completely studied and learned it. So if it was linear, we wrote equation something like that. We had the bias term and intercept term that times to the x. And over here, we also can have the nonlinear one that we can form nonlinear model of the prediction. So by looking at this, for example, on advertising on TV, what we want to do, we want to exactly do the same, but this time with neural network or deep learning even. Are we doing something totally different? No, exactly we want to do the same. So we will see how we can do that. And here you can see the advertisement data that comes from, this figure comes from your book. If you want to answer why we need deep learning, we can say finding manual features sometimes can be hard. For example, in SVM or different techniques that we already studied, we say, okay, if we have a image that we want to, for example, consider features as like kind of people nose, people eyes. So extracting those features are a little bit difficult depending on the application that we have. But with deep learning, we can deal with that problem, how? With creating hierarchy of the feature extraction. What does it mean? It means that we can define high-level, mid-level, low-level features over there, so that if you want to define a face of human, so this face, of course, includes like eye, eyebrow, eyelash, and different elements that we can have in our face. And those, for example, if you consider only the eye includes some circles, lines, and every detail like this. If you put all different lines together, you can draw, for example, eyebrow, or different kinds of circles, different kinds of, again, combination of line, circle, and small shapes. You can form higher level of understanding of the frame. So what we want to do in deep learning, we want to, okay, say, can we kind of learn kind of these low-level features in order to understand high-level features directly? So we want to answer this. Another example, you can consider some kind of animal, elephants, for example. Again, these kind of lines, combination of all these kind of lines can represent the higher level a little bit, mid-level actually, and then higher level that represents an elephant. Another example with the cars, for example, all are again consist of some lines, and for example some objects, chair. Combination of different lines, shapes, small shapes can lead us to understand the whole frame of the image. So if we specifically want to talk about image processing, we want to say, okay, we have image, we want to understand the lines, understand the simple shapes, and based on those simple shapes and the combinations, possible combinations, we want to understand what is the object, for example, in higher level of scene. We will discuss it, of course, how this process is happening, how we can achieve this, and we will see how that is working basically. To understand that, of course, we need to, first of all, start with neural network, and we need to define a neuron or perceptron, simply. I'm sure most of you know, but let's have a look. What is the artificial neuron? We say artificial neurons, also known as perceptron and node, and they are simplest element of the neural network. Artificial neurons are inspired by biological neurons from nature. For example, in the brain you can find it. And how it looks like, you can consider a neuron like that it has three components. Dendrites, that is input signal. So the signal goes as input in your brain. And we have nucleus as computational unit that computes the information, and we have axons that gives you the output. That can be multiple outputs and multiple input over here. So this is what's existing in nature. And with artificial neural network and deep learning, we want to exactly implement the same concept in order to solve the prediction, for example, model that we've had. Linear regression, nonlinear regression, whatever we studied before this lesson, we want to do the same thing with this concept over here. Is it clear? Any question? Good. Let me fix this. I don't know, it's hard to press it. Okay. Now we want to directly go to the having a look at the neuron or perceptron in computer system. We want to implement the same figure that over there I discussed with you. What we want to see, this part that we want to see is called forward propagation. Forward propagation means that we want to give the input and get some output. So data comes from input and forwards pass to the end. This is just the definition of forward propagation. How it looks like at the beginning look, you can see that we have some inputs, different x's, and one term bias. What are these x's? The x's, the inputs that exactly we were discussing all the time. For example, height, weight, size. We were discussing on the plot in linear regression, for example, advertising on TV, each one of these, TV, radio, newspaper. So these are data that you can put values over there. We will see an example. So this input kind of merges with some weights. We want to add some weights per each one of these, plus the bias, and go to calculate the sum over there. What does it mean? It means that, of course, for example, the data advertisement on TV maybe is more important than radio, right? You have some data is coming. You want to learn that TV is more important. How we can learn? We can adjust the weights. So my perceptron kind of is a structure that I want to find these W's based on these X's, that if you sum them up all, I can add some nonlinearity on it. Nonlinearity, I will discuss what is it. Then have the output. So input comes. I want to find some weights and bias and add some nonlinearity and get the output. Now let's imagine I just remove like just we have two of these bias and the one input. It's very similar to linear regression, right? The equation, we had the bias and some thetas instead of w's here, the x, and we get the sum, and we had the sum output. Now we have like a little bit more complex than linear regression, very similar concept. So if you understand those here, it's very simple anymore. But of course we need to add nonlinearity, and there are the reasons that in next slide in a second I will explain why we have it and what kind of things that we need to over there. How the equation looks like, let's have a look. We can say y hat that always is used for prediction of the model, output is equal to, this y hat is equal to, this h is the function of the nonlinearity, linearity that we have over there. We will discuss it as I told you, but look at the whole equation. Beta, not beta, bias added by some of the weighted inputs. So I want to calculate the sum of the all weighted inputs added by some bias, then add nonlinearity. How simple equation it is, you see? Very simple. We know all the components except this one. We will soon see. If I remove this, very similar to linear regression, just we sum up all the different weighted inputs over there. Is it clear? Any question? So now, because you know what is the work of the duty of bias over there, you know what is the duty of these W's over there. W's are similar to thetas over there. That one was for bias, one was for intercept, like the slope and intercept on the model that we had. Let me also draw the plot over here. Now we want to have multiple of those. That is more complicated. For more complex problems. So if we have a look now at details of this equation, we can write this in form of linear algebra and say that these x's and these w's are actually matrices. So that is like nothing, just x is equal to x1 to x to m, and correspondingly, we have w's for each one of the x's, the weights of each one of the w's. So instead of weights, instead of sums, we can write the inputs over there on the matrix. So now the only thing over there that is remaining in forward pass, for now keep in your mind that we are discussing about forward propagation. It means that input comes, we want to see how we can calculate the output. We didn't do anything, we didn't train the network, we didn't adjust the weights, we will discuss these already. But the thing that we've seen, we saw the perceptron, that if input comes, we apply simple equation, then we have the prediction. Okay? And now we want to complete it with adding activation function, that the H that we didn't discuss so far. We say the purpose of activation function is to introduce linearity into the network. So linear activation functions result in also linear decisions. On the other hand, nonlinear activation functions result in approximating arbitrary complex models. Like you can see linear function over here that we discussed, nonlinear function over there that we discussed. So that what we want to do, we want to, if our model, if our network wants to predict nonlinear model, we want to most of the time add nonlinear activation function to our that equation instead of that H in order to do what we want and do the prediction test. That's one note that you should keep in your mind. Then we should say, okay, we want to deciding what goes to the next neuron actually. What was happening? Input was coming, we put some weights, we sum, and we apply some activation function. So that if we have multiple layers, we want to decide what is going outside. With activation function, kind of, we want to control it. Of course, we have millions of parameters. If that network is too big, lots of inputs is coming, and weighted sum can go out of the limit. What does it mean? It means that lots of numbers are coming, and you always sum them, right? And this number can be exponentially too big, can get too big number, because you're summing them up and multiplying with some weight over there. So kind of activation function wants to, one of the main purposes is to restrict the output that you are calculating. Because you have image, for example, and that image, each pixel has some value, 0 to 255, let's say. Then those values comes, multiplies by some weights, then sum them up, then the value gets bigger. We want to limit it with activation function. So in the equation we see that y hat is equal to this activation function. We want to apply it on this simple term bias added by intercept times the weights. And basically we say, okay, practically all the activation functions are nonlinear that we are using. Let's define it. We have a couple of different types of activation functions. You can see, for example, in the left side, sigmoid. So sigmoid looks like, the shape looks like this, and equation can be written as h of the x equal to 1 over 1 added by e to the power of minus x. So it means that the h of x, instead of this x, I want to put this term over here, and whatever comes, I want to apply this equation. What does it do? It means that the input over here, the x, means over here, the x, whatever the value is, can be very big or small. Whatever the value is, I want to plot it between 1 and 0. So, for example, if value in this shape 4 comes, you draw a line over here, and the value is 1. If some value around here comes, the value is like about 0.6. And whatever the value input comes, whatever your neuron calculations, the neuron weighted sums calculates, you put it over, plug it over here, then it plots it between 0 and 1. And this is called activation function. This is one type that plots sigmoid between 0 and 1. The second activation function that we can use is hyperbolic or tangent h. Equation looks like this. Again, we want to give this term over here instead of this x, and this x can be calculated in this equation, and it plots the value. Actually, it maps the value between -1 to 1, in range of -1 to 1. Another type of activation function that is very popular is rectified linear unit, or ReLU. That this is more simpler. Says, okay, h of x equal to max of the 0 and x. It means that this term, whatever you have, if negative value you have there as input, put it as 0. Otherwise, the same value that you have. Actually, it is like removing all negative values simply. And why it's popular, I will discuss in next slide. On the other hand, we have leaky ReLU. Leaky ReLU is another type that is a little bit different than ReLU, that because it allows some value for negative ones and plots it. You can see that is not certainly makes everything 0. It still allows some negative value over there to go through the network that we have. So, any question? Clear so far? So you should imagine everything. If you miss it, then rest of course will be difficult. If you have any problem, just now ask. So we have inputs, we added some weights, we sum them, and we apply one of the activation functions that we want. We will discuss how and why, which one. Okay? Good. Now, first of all, let's discuss the problem that we may have with activation function, and then we can understand the activation function kind of a little bit better. We have gradient vanishing problem, and gradient vanishing problem says that using sum of activation function can result in shrinking gradient and making it too small and vanishing the values that we need. What does it mean? It means that, let's say, so we said we have some x's as input, and we calculate this weighted sum, then we have some output. Now, if we have a couple of layers of these, more layers of these, and we map every time, then your data, whatever it is, gets smaller, right? Because that for example, sigmoid, if we are using sigmoid function, every time maps all the data between 0 and 1. Then every time the data, the value that you have is getting smaller. And maybe after some time you have some calculations that is useless because the differences is not too much meaningful for you. So that's called gradient vanishing problem. That some of these activation functions in some problems may stuck in. So especially this is more common in activation that decreases gradient exponentially, because the value can be between -1 million, 10 millions to positive big value, but it decreases quickly to between 0 and 1, for example. As I mentioned, sigmoid function has that problem. Hyperbolic can have that problem because this also plots everything in between range of -1 and 1 too fast. So what is the solution to this problem? There are two common solutions. One solution is using another activation functions that has this problem. One of the most popular activation function for neural network and deep learning, as you may know, is ReLU, rectified linear unit. Why ReLU has not this problem? Because although removing all negative values, kind of we can say those are bad values or not very useful values, negative ones. We can kind of ignore them. But the positive ones, we are letting to flow in the network. We don't care about it. So we are not shrinking, or we are not reducing the size over there. So you may say, okay, we had a problem, we solved it, now we again allow some activation function that has the same problem? Yes, we do. Because again, the sum of the weighted values can grow exponentially over here, right? Like the output of value, the output value of the network can be 10 million, 100 million after those big ones in here. But we have another solution to settle this problem over here too. I want to mention, it doesn't mean that although we are talking about gradient vanishing problem, but gradient vanishing problem is not certain to happen every time in all problems. So gradient vanishing problem can happen sometimes. It's still sigmoid function, hyperbolic function are useful, can work very well in many applications. But sometimes we can have this problem over there that we need to, because of that, mostly ReLU is more popular. So the question is ReLU linear? Because it looks like linear line over here, but of course it is not, because it has continuation. So this is like you should consider all together, so it's not linear. ReLU is non-linear. This is common mistake that some students do, and they think it's linear. So we can conclude that ReLU is computationally efficient because the equation is too simple. We don't need to calculate anything, just max of the 0 and x, that's it. And it helps to solve the gradient vanishing problem. Second solution is to solve this problem is keeping some connections, that this will be more understandable after some time, but keep this in your mind that we can skip some connections. It means that if you have input neurons, and if you have another layer that we will soon discuss, skip connection means that not remove connections. It means that we can connect some of the nodes, some of the layers to other one. We can pass data, we can let the data flow to the next layer directly without applying activation function and destroying the data. And if you do this flow, go forward, then you don't have gradient vanishing problem because you let the data to pass much more. It's like creating big streams of data to go to the end, not reduce so that it can vanish at the end. Is it clear? Okay, so on the other hand, as I mentioned, there are some disadvantages for ReLU. because there is no limitation of the output on the positive values over there. You can see that whatever comes floods to the end. So x comes, whatever it is, it can be infinity. What is the solution? How we can control that if we want to use ReLU? There are different techniques. One of the most popular, famous one is the batch normalization. So you are familiar with batch size. We discussed it already. Now you should connect that to here too also a little bit. But in batch normalization, we say we can normalize the inputs of each layer. So to do this, we can compute the mean and variance of the whole input as mini batch. So we call it as mini batch because it's part of data. Because if you have a data set, like 1 million data, each time you are giving, for example, one sample data to your network, right? And if you give 100 of those, we can call it as mini batch. 100 of those comes to the network that you have. So that's called mini batch. And if you can calculate the mean and variance of that data that you have, what you can do, you can normalize it. You can normalize the input based on mean and variance that you can calculate to mean 0 and standard deviation 1, for example, in this case. So the data distribution. You can consider like data distribution is whole this table. Data can be spread over there. But what I want to do, I want to normalize. I want to say this is the mean, mu, and this is the standard deviation. Wherever it is split, I want to keep the consistency of the spread, but I want to bring it into this area. That's it. That's called normalization. And you kind of now limiting if the ReLU, the data, what is happening with using ReLU, spread is get bigger also. The data, the output of neurons, the values are growing. So every time, or in some output of some layers, you can normalize it again, bring it here. Then let it grow, then bring it again to the small part. So that's called batch normalization. We normalize the data. So we say it can be used in several points in between the layers, and it's not must to use. You may don't use it. You may put in different layers depending on the data that you have, the growth that you have, the network size that you have. It can vary. Now the question is maybe from you guys that, okay, we say that here we can compute the mean and variance of the whole input mini batch. But mini batch A, mini batch B, mini batch C, the values can be different, right? Mean and variance. Because the data are different. The mean and variance can be different. Is that problem for us or no? People who studied deep learning course, especially, must answer. Answer the question. Don't think too much. Is it problem or not? Yes? He says yes. Who else says yes? The answer is no. Not yes. Why? Because we don't care. We say like table 1, this is whiteboard, consider whiteboard, and data is spread among all data in one mini batch, right? The next mini batch spread can be different, it's smaller or bigger table or a smaller table, they spread, right? Mean and variance can be different too. Whatever it is, I want to plot it to this one, right? I don't care. I plot all to this, and this is the advantage that we have. The spread, the mean variance can be different, shifted, wherever it is. For example, for one mean can be here, the other one mean can be here. I want to plot it all here, then mean will be here, mean will be here. So that's one. Second reason is generalization. When you have like different kinds of those mini batches with different mean and variance, your network becomes more generalized so that understands different new data may come to the network. If new data in data set comes to your network, can make better decisions because they can see variety of the input over there. Then answer is no. So, and this is one advantage that we have over there to apply batch normalization. What is the a batch normalization solves, of course, this problem that we don't need to deal with it too much. Now let's make everything more clear with seeing some example. So we said that, okay, we have the perceptron, we have some inputs, we want to have the sum and the output. Now we know what's the nonlinearity activation function. So what is the idea, what is the purpose? We want to have prediction, draw a line for data. So very similar to linear regression, we have bias, we have input, we have, for example, two inputs here, two-dimension input here. We calculate the sum of them, apply some activation function, and get the prediction hat. So let's put some example. Let's say we have some random values for bias and W, as we were doing in linear regression. So something random. I put bias 1, and the weights, we don't know, just 4 and -7 for these ones. You can see. Okay. Now, what is the equation that I need to calculate is this one. I want to calculate the output, y hat, prediction. What is my network, this simple neuron prediction for me based on this weight? So let's consider, then I can replace the equation. I can write like the activation function I will apply at the end. 1 bias added by the inputs that I have, whatever can come, times 4 and times -7 times the weights. So if I apply this, I can write a simple equation, right? Y hat is equal to h, 1 added by 4 times x1 minus 7 times x2. So this represents a line in 2D. That exactly we were doing in regression. Actually, I can show on this slide. I have it here. If I draw this is a line, right? This shows me this line. And this is what I want to achieve in regression model or the network that I have here defined for me. Now what I want to do, now I want to kind of adjust these weights so that for different inputs, this line can fit for the model that I have. All the problem that I want to see is figuring out these parameters over here, exactly same as linear regression. So now let's say if we input the x, so one sample data comes as input inside, x1, x2, like we need this one over here. So we have lots of data, x1, x2, one of the samples. I pick one of the samples and give it as input that this sample is over here, for example, minus 4, 6. Then what we calculate, I just replace it into equation over there. 1 added by 4 times minus 4, and we calculate it. Finally comes minus 25, the calculations. Now, the only thing that I need to apply, minus 25, should be applied some activation function. Here I applied sigmoid. If I apply sigmoid minus 25, then the result will be 1.38. It will be plotted over there. So now let's see another example with 3 inputs. 3 inputs coming, getting sum and activation function, the output. I can calculate the same. I have 3 random weights over here, 1 bias. I can write the equation. The equation now here will be looking like this, the x's and the data. So actually, this example here is with 4, but here I have a 3. I should sync it. So anyway, I think the calculation will be with 3 by the way. Yeah, so that one I should fix it in these slides. So 3 inputs, y predicted tag. So now, because I wanted to plot it in 4D, I couldn't plot it. Then I removed it to change it to 3D. So now this is a hyperplane that we discussed already also in separate section. This hyperplane is decision boundary that I can draw. And if I draw it, the hyperplane looks like this. So the hyperplane shows my prediction that I want to again find the intercept and slope, or the weights instead of slope, w's, to find it properly to fit my data. We will see how to do that. For now, we are just seeing the calculation of forward, just my network prediction. We haven't improved it. We haven't discussed it how to train it. Now what can I do? I can write, okay, let's write instead of whole this part, z, to make equations more formal. This is very common to do in neural network. We can say the input, the weights can come to the z, so that y is equal to h of the z simply, and z is equal to the equation that we had. Just instead of this equation, I'm writing z. So that now, instead of one output, one prediction, we may have 2 predictions as output. We want to predict 2 outputs, not 1, based on this input data. What can I do? So I can connect not only all of these to one z, the other ones also to z2, to other one. So that for each one I can calculate weighted sum of the intercept and the slope. The note is that the weights are different, of course. For z1 we have different weights, for z2 we have different weights, that we should figure it out. Then I can write the general equation. Zi is equal to bias I. The i's indicate which one of the bias z1, z2 it is. And j equal to 1 to m, xj, w, ji, that represents each one of the weights and data that going to the flow. So all of these explanations can be implemented in one line with library, using library of the torch. So you need to import torch.neural network as neural network. Then we can define one layer, layer 1 equal to neural network dot linear. So linear means that like we have linear connection over there. With the input, how many inputs do we have? 3. You see 1, 2, 3. 2 outputs, 1, 2 outputs, bias true, because we had the bias. And if you apply this, exactly this equation will be calculated on your data, 3 input, whatever you give as input, then it will give you the output, will calculate for you. Is it clear? Any question? So for now, we didn't learn how to train it. We learn how input comes, how we calculate the output. This line do that for us, and this is the equation simply. Can we add many layers of this? We will discuss. Yes, we can. You just copy paste this line, and the output will be connected to input. Output will be connected to input. Should be just the size should be fit. So sorry. So for neural network, we have universal approximation theorem. Let's define it. We say in practice, neural network with minimum one hidden layer is able to approximate any functions almost close. This is very interesting to know. We know deep learning, we know multi-layer perceptron, we will discuss it, we can add many layers, but the universal approximation theorem says if you have neural network with one hidden layer, and if you have enough proper amount of neurons, and if you have proper activation function for that neuron, it gives you something meaningful. It gives you kind of good approximation. You don't need to make it very complex. Actually, it works. Kind of, we can say how complex the problem is. With one hidden layer, you can make it work. Why we have deep learning? Why we have more complicated networks? Because we want to make the accuracy high. We want to maybe, like this still works, but we want to make it 99%, 98% accurate, not like 60%, 70%. So this is famous universal approximation theorem with neural network. Now let's talk about the typical training procedure of neural network. We say we have learnable weights in neural network, W's or parameters that we want to learn. We want to feed input through the network to pass through the output, of course, at least one time. Then based on that, we want to compute the loss, compute the error. So we give inputs, and we have some random weights. My model gives me some y prediction. So y, what was the y? We had the y hat as prediction. But let's say we have supervised learning, and we know the true label. We know what is it. Now, of course, my model is wrong, right? This is the answer. This gives something like, the answer is like, for example, 1. It gives 0.1. This is wrong. And now I need to calculate the loss, kind of, and use that loss to update the parameters W that I have. That's like very simple concept. Similar to what we were doing, if you remember lastly, that we will use it. So we say we want to propagate gradient back into the network to calculate the parameters. So we have the error. Based on that error, we want to kind of forward it back to update the weights of the network, the W parameters, in order to improve it. So for updating weight of the network, what we can do, we can write weight is equal to weight minus learning rate times gradient of the loss. Isn't it familiar for you? W hat equal to W hat minus some learning rate and gradient of the loss. Isn't this familiar for you? I'm sure all of you know it. In statistical gradient descent, we did this. In linear regression, exactly we did this. Is it different in neural network? No. Is it different in deep learning? No. We want to do exactly the same thing. And that's why we were studying those to now you can see very easy. We need to calculate the loss, the error, and update the weights. Now let's see how it can work. Okay. My buttons are not working now. First of all, we can say, of course, we can have multiple layers. This is the input bias, the data that comes. We have one hidden layer. This is called hidden layer in middle. The nodes that I have, then the output. so that I can name it. This is like bias 1, 2, 3, 4. These are the weights that I can count based on that up to M and H1. Then these are called Zs. This Z is that equation that I replaced. And finally, based on that, we have the output that we saw how we can calculate. Now we can have a figure of how we can write the Zs. Z of I, for each one of these Zs, I can write this equation. Bias added by some weighted inputs, same equation. But how can I write the Y? The Y hat or prediction output is like applying the activation function, the second bias layer, this one, second one, and some of this activation function on the Z on this calculation. So actually we have this layer over here. This layer goes to my hidden layer, one hidden layer. Then I can calculate the each one of Z's and apply on them to getting the output. So the output will be based on Z, and we can calculate it. I think should be very clear, and this is one complete single layer neural network that you can use it for train to predict something. Here I put some example. For example, if you want to calculate Z1, this Z1, this line over here, the equation will look like that. Sum, I opened the sum only. Sum of the first weight, second weight, third weight. Simple. To do that, what we can do to have a complete network, we can write two layers, as I said to you. You can copy 3, 4. I think it's based on this 3 input, 4 hidden layer as output. Bias is activated. This is called first layer. Then we have second layer. The second layer output is 4 as input. Be cautious that these 4 must be the same, because the output you have 4 nodes, and here should be node, and the like output of this connected to this layer, and then again output of that layer that is input of the second layer should be 2 over here, because we want to predict it. So if you look, you have 3 layers maybe here, right? Input, hidden, output. But in code we write 2 actually, in fact. Is it clear? Also, this makes some confusion for students. Input, output comes to that next layer, and output of that layer is the Y's that we want to calculate. And equations in the previous slide, simply, nothing specific. If you want to add more layers, hidden layers, it's simple. Now we can add it. Just copy more and k layers, and you can calculate all of it. And if we have less layers, we have simple neural network. If we have too many layers, too much layers, we have deep learning, deep neural network. So we learned the neural network so far, forward propagation. We say if it's big, it is deep learning for now. Okay, clear? How the equation looks like, we can write a general equation for each one of the z's. That is, that just works with indexes and can show the same calculations. Z of k minus 1. That shows each how can be calculated. It's general equation for the calculations of the layers. Exactly the same thing. There is also the code for this network, layer 1, 2, 3, 4, and you can see that I've written the parameters m input, because x of m, and h1 is the output of first layer, how many the size is. I put some variable over there, h1, hidden layer 1. The output size is input size. h2, same, hk, and finally 2 node design. And you can add more layers, then we have more deeper network. Let's quickly have a look at numerical example. The question is, okay, let's imagine you are a swimmer and trying to practice for participate in a competition, and you're practicing. And the question is success. Are you successful in, will you be successful in swimming competition or not? And we want to have neural network model that can do the prediction for us. What we can do, we can write x1 equal to the parameter 1 as input, number of hours of swimming practices. Then, then x2, parameter 2, number of hours that you are practicing in dry land, outside of the water, some body exercises. So we want to consider each one of you guys based on number of hours of swimming practices and based on number of hours of dry land practices, will you be successful or not? So now you may say, okay, how neural network can do that? Of course, we have a data set. That data set has some people already, sport guys. We know that how many hours they practiced and are they successful or not. And based on that data set, we want to train our neural network model, and then later ask each one of you from that model that if you will be successful or fail. Okay? Of course, we can add more parameters, but for now, we want to just understand based on these two. Let's plot the data set that we have. We can say x1 here is number of hours of swimming practices inside water, and this is dry land. So how much? And based on the data set that we have, we say these blue ones are the winners. And basically, you see who practiced more in both are more likely to win the competition because their body is more ready. On the other hand, the losers are these red ones. And if we now consider you as sample, over here, now my network needs to predict it in classification task, which one the class is belonging to. So what do you think about you? Any of you can be in the blue ones, success ones, in swimming competition? Any of you is good in swimming? No? Okay. Yeah, I haven't seen you. I haven't seen any of you in swimming pool. Yeah, that's the reason. Okay. Now, let's have a look at the untrained network. We have this network. Now, why this network? Because we have two inputs and one output. Two inputs, I put it three nodes in hidden layer. Why three? You can change it. You can make it bigger and smaller based on the problem that you have. Usually, is like some kind of rule is that number of inputs plus 2 to 5 usually is enough. If you have two, if you added 2 to 5 numbers as hidden layer, usually is able to calculate what you want. If you have 1 million, then it will be 1 million like plus some value. Now, the same example, the same sample data at 3329, I want to feed it to my network. So the weights are random so far. What is happening? So 3329 comes to x1, x2. Then I can calculate it. After the calculation, the equation that I have, the output will give me some value, 0.1. The math that we did exactly. This is our prediction. The prediction most likely is wrong. Why? Because after training, we're supposed to see 1 over there. So the value should have been 1 as successful, for example, for that data. But here is 0.1, something wrong because the weights are not trained so far. So what we need to do to train the data, to train the network, now using this prediction data, we need to calculate the loss or error of the network. I already mentioned you here the loss that we have, but formally let's see how we can calculate it. Similar to all problems that we had, we need to have loss function, and here we can write it in this general form. What is it? It's very simple. Nothing specific. We want to calculate error of the weights. Error of the weights. We can write error of the weight is equal to the loss function, which usually is common to show it with L or loss. Loss function of the function f, that this function f is the prediction, this y hat over there. So it's common to show it, like we could have write y hat over here too, simply as I did there. But in neural network it's common to use f of the x's and w's, the function that gives me some prediction, and the label data. So we are still talking about supervised learning. We say that we have the label data and the loss of that one. Is it clear? This is general equation. Now what we need to do, instead of this loss, we should write some term to calculate it for us, that we have different ways. For example, what we have here. So here first I show example. So let's consider that x are these values, that coming like the set of pairs of these values, 33, 29, 28. So these are my data set that one by one you need to feed it to there and calculate the loss. And if you want to calculate loss for whole this data, we can get average of it, 1 over n of the whole loss as average for my whole, for example, mini batch that I'm feeding to my network. Because we also prefer to apply it on average of the error, not update it that fast. So one of the ways of the calculation, we have different loss function. The simplest one is the Euclidean distance. This is the Euclidean distance that we studied many times. The Euclidean distance between the prediction and the label. That's it. So my neural network loss function based on prediction, based on the predicted data and labeled data, can be written as a code like loss equal to loss neural network mean square error loss. Then output is equal to loss of the y and prediction. So this simple line will calculate my network error based on the x's that I'm giving and based on the outputs that my network predicts. And this is the, for example, true labeled data. The differences of this and that in Euclidean term gives me my network's whole error. Any question? Clear? I think should be very simple and clear for everybody. Why we are calculating loss? We want to use it to update our weights. So you can have 5 minutes rest, then we continue to see how we can update the weights. All right, everybody, pay attention to continue. So what we've done, we calculated the loss function so far. One of the examples of the calculation of loss function can be Euclidean distance. We have many more different metrics. We have studied, like, for example, in linear regression you have seen. One of the other metrics that is also important is cross-entropy loss. Cross-entropy loss is useful when we want to have probability of prediction as output between 0 and 1. So if the output that we are expecting is like 0, 1, 0, 1 is like binary class, then what we can do that is very useful in classification tasks, then we can use cross entropy that computes the differences of prediction and the true labeled data. The equation looks like this in log form. I don't want to explain exactly why exactly this is in this form and prove it, but in cross entropy the objective is to calculate the very similar equation that what we've already studied, like with log form of the equation that we've had. So f of the function that is prediction added by the reverse of the label, the data. This can give us the average of that can give us the error of the weights that is based on the 0, 1 or classification task error. So when you usually have classification tasks, for example, you have a couple of hundreds, thousands of images, then you want to say that, okay, this is belonging to which class. That's what we usually do. We can like each output, this can be, it is common to determine like the output 1 is like cat, output 2 is dog, output 3 is car. We define output for each one, then the output will be, the one will be the one that is in the class. Like if the picture shows cat or dog, then that corresponding output will be only one. It's common to implement for classification tasks in neural network. So in those cases that labels are true, false, we can use cross entropy equation as you can see over here. And in Python is very easy again. We write loss equal to neural network dot cross entropy loss. That's it. Then it calculates this equation for us. Then we can apply it on output. Any question? Clear? There are many more, but I'm not going to explain all, two common ones over here. Now we want to see, okay, using the loss and using forward propagation, how we can update the weights. General rule is we want to find the network weights that is minimum. So W star shows optimum weights that I want to find. So that what I should do, the argmin of the loss function, we want to minimize the loss function. The error goes to the lowest possible values that we have where their W's, and the whole equation can be written in simplest form. The optimum weights equal to argmin of the error. I want to minimize the error. Minimization of the error, if we plot the values, weights, like this is W0, this is W1. Don't mix it with the hyperplane that we've had. This is for the W's, and this represents actually the loss function for me. So what I want to, like this is whole possible errors that I can have. Initially, the error, the network that you have initially, error is somewhere random, usually very bad, right? Because the weights are random. What we want to do, we want to optimize the loss. If we want to optimize the loss, what we want to do, basically, we said that there are different approaches to do that. For example, in gradient descent, we can find the gradient of the error that we have. This point can be calculated by gradient, then we can optimize it. So how it can be done? For loss optimization, we want to make the error lower. Then we have learning rate as a step size to jump to the next step, then jump to the next step, then jump to the next step until my error goes to somewhere that is minimized, goes inside, and this is like minimum of the error. So I want to find best W's, best W0 and W1 if I have only two, to minimize the error of the network or model that I have. So this is visualization of what we want to do as optimization. But how in practice we can do that? We can apply exactly same gradient descent algorithm that we studied. We studied, we implemented, we practiced gradient descent and linear regression, exactly same algorithm, will work for neural network. This time for finding W's of the weights of the network. How it was to review initialize weights, loop until convergence, compute the gradient, and update the weights. Weights equal to weights subtracted by learning rate by gradient. How we can do that in Python? Again, 2 lines of code. We can write the torch.optimum.sgd, statistical gradient descent, or gradient descent can be 2. Model.parameters as input, learning rate as input, and momentum, how fast that learning rate wants to move toward that direction, the speed of the movement. All can determine my optimizer. Then my optimizer.step will run it 1 step for me so that I can do this procedure in a loop to optimize my gradient descent. Now we want to know about backpropagation, how we can update the weights. How that is working? We can say, okay, backpropagation updates back the weights, as I explained, and we want to calculate the gradient of the loss. How it is, if we have a look in only one line of network, to make it simpler to understand, one x, one z calculation, and one y hat. How backpropagation is working? So, if you remember in the statistical gradient descent, we needed to, based on the loss, calculate the gradients of the error. Gradients of the error that shows how fast error is going down, or that, like that. So, in neural network, we should do it per layer. It's not like calculating once and applying. Per layer, we need to update the W's. How it can be? So, based on the output, I can write the equation over here that you can see. I can calculate the partial derivatives of the, if I want to calculate this partial derivatives based on this W2, I can write the partial derivatives of that based on the W2 that includes the first element, partial derivatives of the W2, and the second element, partial derivatives of the output layer that I have. So per each one, I can calculate it. Now, what if I want to calculate W1? Now I can only include this W1 as partial derivatives over here, this part that I've written as Z1. So this can be done, but in Python we don't. This is what's happening in background to update the weights. But in background, but in PyTorch we don't need to implement it. It automatically, when you write the step, it automatically can be applied on your network. In other libraries you may need to implement it, but here we don't need to write it. You just see the partial derivatives calculations. And what was it? Again, as reminder visually, simply when you have like this, we want to find the slope of each one in order to use it for learning rate update of the weights over here. Computing gradients, visually you saw, and then update it. Now, as you know, we have learning rate challenge. We already discussed it. Exactly same challenge in linear regression is also existing here. If you have a smaller learning rate, then your step size is too small. This is the error. We want to minimize it. This is the best point that we want to achieve for our model. So if the step size is too small, it takes too long to train it. if the step size is too big, the jumping problem that can happen in neural network too. I gave you a code that in regression it was jumping, you saw it visually. So here the same thing exactly can happen. So learning rate should be also adjusted. And if we have a stable learning rate, then we can avoid local optimal or convergence problem repeat. How we can solve that formally? Okay, because when you were like changing the parameters of learning rate, it's a little bit difficult to adjust it. There are some techniques that can also be helpful for you. We can like one approach is that what you've done already with the codes, you tried different learning rates. It's common to try different learning rates. Another way is using the adaptive learning approaches that can adapt the can adapt during the learning rate itself automatically and can be helpful. Still, you may need to adjust some parameters for that, but it dynamically can adjust learning rate for you. Adaptive learning rates can be methods that automatically works based on the gradient descent technique and at the same time tries to adjust it. And of course the goal is minimization, and it's dynamic depending on the dynamicity of the adaptive learning rate is based on the gradient size, momentum of the learning, the particular weights of the size. I don't know why this is not working today, and different elements. But finally, you can see some techniques that we have here. That for example, the ADAM is adaptive learning rate that automatically can adjust the learning rate for you to make it easier to train. We have SGD, we have studied it. You exactly know how it works. How we define it, we write optimizer equal to torch.optimum.sgd, then model parameters that you define for your model, then you define the learning rate that you want. For ADAM, the same, torch.optimum.ADAM. For AdaGuard, another optimizer that we can write torch.optimum.AdaGuard. Torch.optimum.RMSprop is another technique for optimization of the error of the model network that we have. So now you may say, okay, we studied this, but we don't know this. The approaches are similar, just a little bit the techniques, the equations, and how they applied are different. If you are interested in, you can study how they are working, and specifically how adaptive learning rates are working, how they can use these elements that I explained, gradient size, momentum of learning, and particular weight of the size can be applied inside the library itself. So this is your task that you need to, if you are interested in, do that. It's not must from my side. So any questions so far? Is it clear? So we forwarded and calculate the loss, and we backwarded and updated the weights. How? With SGD, for example. We will see how it works in loop as an example too. I will show you some implementation. So gradient descent reminder and the problem that we had, that we said that it is computationally very expensive. We have exactly the same problems here. I have these slides over here again to remind you that what we've studied working now over here is stochastical gradient descent. We solved that problem, and most importantly, we said that SGD with mini batch we should use. That is very common to be used in neural network and deep learning. Mini batch is very important. Why? Because of the reason that we discussed already. The computation of the gradient is expensive over there, and we wanted to calculate based on the batches, not one point. We said that if we calculate based on one point, then the model will be like, if I calculate based on this point, will be dramatically changed. I rather to calculate it based on batch of data and update the weights of the statistical gradient descent. I don't want to explain it again, but it is very important. All the same concepts, all the details that we discussed in one 3 hours, 2 hours lesson are existing over here for training neural network. Based on that, if we continue, also we have overfitting problem here too. We discussed it many times. You can see underfitting problem here. This model, the blue one, is the model that we have, and this orange one is true. The model is underfit because it's not predicting good the data. We have here the good fit, ideal fit, that the blue one is fitting very well. But on the right side also we have overfit. Overfit shows that the model learns exactly each data, that we are not preferring these two. We said that we want to have bias variance trade-off, and so that we have ideal fit. Exactly all the things that we explained again is valid in neural network and deep learning. Then we also mentioned regularization. We said that we want to do regularization is more important and common to be discussed here in neural network. Let's see how we can do that. We say it is a technique to prevent overfitting, and we can improve for unseen data the prediction. How does it work? So if this is the network that I have, the connections from input to the output. With regularization, I can apply some techniques. For example, I can remove some of the nodes randomly every time. For example, 30% of the nodes, I can put the weights of the networks as the calculation as 0 randomly. So that what is happening over here, my network cannot memorize everything. Sometimes forget some data in the middle. And that forgetting causes that your network is not overfitting to your training data. It's like human. You sometimes forget something, right? Then that's happening over here by purpose. You want to say forget something in middle so that the weights are not very well. You make them worse sometimes randomly. So this is called the technique of regularization, and you can implement it like this. Neural network dot dropout. P equals 0.3. It means that 30% of the weights of the nodes will be equal to 0 in middle, because when you are calculating your optimization, W's are getting better, right? You put you're finding these W's, W1, W2, 3.2, 2.5. Sometimes you remove and put it 0 after training. Is it clear? Any question? So this regularization is like also can be plotted in the similar figure that we discussed many times there. Your model is starting from here, the calculation goes to the right side. This is underfit, and at the point that it starts to diverge, like the model gets worse, then we have overfit over there. This line is indicating my best parameters to stop my training. So this one is test data, this one is train data, and indicates that where my model should be stopped to be trained. Why this is always going down? Because it is my training data. The error gets down. Why? Because training data, my model always sees my training data, then always gets better. But why this is getting worse? Because this is data that my model haven't seen. This is new data, never seen. And when you try with new data, then you, in some point it starts to converge. Not converge, diverge. It starts to get worse. Any question? So here you can see another figure. We already discussed this figure. Again, importance is here that the flexibility model, these are different models, and you can see like when the flexibility is increasing for training set, my error gets MSE mean square error gets lower, but for test it gets worse. So each one of these red can be like each separate data point over here can be a new model that you can see. In some point the models get worse, and this is the point that you can achieve the minimum test error for that model. This line is indicating that minimum error that you can achieve for mean square test error for test data. But of course this can go toward even zero. Zero means that your network memorize everything, exactly what is the input, what is the output. But for test data, then it's not working anymore. Any question? Same problem we have in neural network and the same model. So now let's have a look at ImageNet, one of the most popular visual data set that we have. It is for visual object recognition. You can use it. It has 14 million images that have been hand annotated. It means that somebody annotated, and it has 1 million annotation means that says like this is cat, this is dog, this is train, this is bus, this is car, and it has 1 million image including the bounding boxes. Bounding box means that you have a frame of image that you can exactly determine what is there. That in image processing task is very common and important to have it. It means that if you have a frame of image, picture of something, then you have like a person here, then you have a car here, you have a tree here, not good painting, but anyway. So bounding box means that you have these bounding boxes, like the address of the x1, like x and y of the one, and x, like we can say x of the end, ex. This is the start and end of the x1 and y1. And the bounding box indicates that start and end. Again, start and end. Again, for this one, should be somewhere from here to here, the start and the end. So they have it for you already, so that you can take it as labeled data and train it. And you just say, okay, this is car, this is tree, this is human. Then you can use it to train your network as deep learning model. But if we have a look at the different architectures that we have there, we will see in the rest how deep learning is working, how convolutional layer is working, how the general perspective is. But this is the most recent update. You can check it on the website. We have top accurate models. These are all different networks for deep learning models. You can see from AlexNet, you can see the VGG, ResNet, very, very popular ones, up to very recent ones, that is, like, for example, Coca, very popular one to be used. Different architecture of the deep learning networks that we will discuss how they are looking like and how they are working. If you propose a model, maybe it will be somewhere here. If it's good, then you can push it up. If you can push it up, that's very nice. You can see that this is the pushing up, and the accuracy gets better. Any question? So these are all models that during time we've seen and we've had. I will open it later on what is going on. For now, we've seen neural network, and we said if we have multiple layers, we have deep learning, but for deep learning, we have lots of things to discuss that we will see. So when we are talking about image and visual information, in visual data, we have feature extraction. That is very important. That indicates what is the in visual what we have there as feature extraction. But that visual information can be represented usually as arrays of numbers. What does it mean? That you may sometimes get confused is like when you have RGB image, so per one image we have data for RGB, that each one is the value that separately we can also indicate them. It means that like you have a frame, for example, a picture like 400 times 800 pixels. If it's RGB, it's time 3 because 400 times 800 pixels, per each pixel we have 3 colors, and each color can be the value between 0 and 255. So this is whole dimension for one RGB image that we have. So for another example here, if it's like grayscale, we don't have color anymore. If you consider it's like 16 times 22, we have only one color, so times 1 times 255. Because each color in grayscale can be valued between 0 and 255, so that now we can consider each one of these pixels for our neural network or deep learning as a feature as input. In the examples that we were talking mostly, we were talking about, like, for example, height, weight, price, or something. But in image processing, we don't have those, right? And in deep learning, we want to consider each one of these pixels as one input. Now you see how big it is. Like just only feeding this colored or even the grayscale one, the dimension of the input, number of nodes as x as input, is this big. So my network wants to learn the parameters, wants to learn millions of those weights that we explained together in order to understand what is happening in this picture. Of course, we can apply it for classification task. For labeling, we discussed it already. This is classification task that my data can be split into 2 parts. We can use it for regression task, the models networks that we have. We discussed it already. We can use it for localization task in order to find these bounding boxes. You can say, okay, my network wants to find the bounding boxes. Where is the start and where is the end? How we can do that? We have network architectures. We have, for example, YOLO algorithm that has specific network architectures, because not only solve the classification task, but also say where is the starting and ending of the bounding boxes. So if we had time, we could have a look at the YOLO architecture later on, but let's see. I have some slides for that. So here how it looks like when you have one image, the grayscale image, you can say, okay, this image can be can be flattened to array of data, and those array of flattened array of data can give me also uh, some some normalized values or some uh, some values that I want to predict depending on what I want to do. Localize and classification, you can see I ran YOLO a long time ago when it was very new. On the you can see that detects me and the chair and everything on there. For example, clock, and determines what is the each one of the objects with network that we can have. And as I told you, that's the figure that I tried YOLO. I will discuss it a little bit today. But let's now come to the point that we say now we know about the neural network. We know about deep learning that in base simplest concept we have multiple layers. We know the evaluation, we know the optimization, we know the loss function and everything. Every necessary things we know. Now we want to say, can we use high-level feature extraction to understand the data that I have better instead of saying that all the inputs I want to calculate weights, end up with some output. Can I say, okay, in these first layers or in the beginning, can I extract first important features, then train something meaningful over there? The question is this. And the answer is yes, we can do that. And now we want to see how we can do that. This figure, we can say, okay, we have a deep neural network, and I want to feed all these as input, and I am expecting something as output. That's possible. But better way, say that, okay, so since this feature I know that has like eyes, eyelash, mouth, all the features, can I extract those first then? Then train my network? Yes, we can do. Or for example, in case that there is a motorbike, you can see that the features are clearly indicate that this is motorbike, and if we can do that, extract both of these together, you can see that we can easily distinguish that this is human if we can see these, and this can be motorbike if we can see those. In case of car, a little bit similar to motorcycle, but still some differences. For example, here we have doors, window frame, the headlight. In solutions like SVM, if we wanted to solve this problem, what we should have done, we should have extract these features ourselves. We should have write some filters, some codes to say that this is I, to detect it. All researchers were doing all the time. So you can write some codes that to detect this is real, if something is round or something, some mathematical calculations like half transform or something to calculate. But now here we want to say that no, let's use deep learning models in some structure that we are going to define in order to extract these, then combine it with neural network that we learned in order to predict the output. So what we want to do, we want to say, as I explained, for manual feature extraction, we need knowledge of each domain. So not only in the image processing that you can see clearly, some domains we don't know what are the features to extract, it is difficult. Feature definition for each domain is also tremendous and very difficult. For example, one, A, B, C, D, you should do it manually, that's more challenging. And feature detection and classification is more harder. So the main problem is that we need a lot of efforts, and maybe we have the image scale, deformation viewpoint, the noise, illumination, and different problems that can happen on the image that your code that you've written may not work. For example, if you say, like, if you want to detect with some heuristic algorithm, some if-else algorithm, you want to write some code in the image to detect an animal, you may say, okay, animal has one head and 4 legs mostly, and 4 legs are touch the ground. And with this technique, search technique, you can easily detect it. But maybe that animal like rotated up to other side, up down, playing around. Then your algorithm won't work anymore. You try a lot, you find the idea, yeah, the human, impossible, my leg always on the ground, but then you should also consider this situation. In illumination, you can clearly understand this is human, we are smart. But now you've written some algorithm to detect eye, nose, ear, but here there is nothing. Then your algorithm won't work. Deformation. You see that it's deformed, like the arm is bigger than head over there. You say, okay, there is something wrong, this is head, like this, but you say that this guy has 2 heads now over there. So these are the problems that if you want to write manual codes to detect the features from image. Instead, what we can do, we can use the high-level feature extraction and that also known as convolutional neural network, that all of you most probably heard about it. Those who studied with me last semester, also you studied this, you know it. Should be clear, but let's look at the details and later on see how we can implement based on one problem from Kaggle. So the idea is to learn features in hierarchy from low level to high level. We are not limited to images, not only over there, but as you can see, we want to say that, okay, the lines, the points, and everything, these all small features, every line, every point can be important for me to extract a little bit mid-level, like with combination of these, I can have eye, and combination of that, I can have face. So if you have a look at this image, if we use fully connected network, what is happening? The n times m, the row and column, can be flattened first of all and given to the network, and the output prediction can become. So there is a point over here that when we are connecting an image frame, so you need to flatten it. It means that so it should be in like columns, all of them. You move all of them to the columns, and the pixels are in column. You may say, okay, then it is harder to understand. No, not for neural network. For us, it's better to understand in this form. For a neural network, so it will be like all in one column or all in one row. That doesn't matter. We just feed it to our network, and our network will learn it. Now the question is, as I mentioned already, so can we replace this fully connected one with some better structure? Yes, it is. And we are going to learn how we can use convolutional neural network and how these steps can be happen to solve our problem. So any questions so far? Clear? So there are 2 sides now. You completely know or you don't know nothing. Okay, hope the first part is clear. You know all of the concepts. So with the convolutional layer, we say we can connect paths of the input to the single neuron. And we call it a sliding window. And what does it mean? Let's say this is the image. And each one of these is 1 pixel. Each one of these is 1 pixel, and let's say it's in grayscale. We just have 1 value per each. Now we want to see with convolutional layer what is the sliding window. We need to understand 2, 3 small things to understand whole convolutional layers. So what we do with a sliding window, we say we want to define a window on this image and say from this part of image bring some important information to just only 1 pixel. Actually, we don't have pixel, we have weights and the inputs, but basically for simplicity I explain like that. So let's say we have pixel from whole this area of image. I want to say what is that important that I can bring it here. Then I want to continue this, and I say what is the important from this area over here to bring it here. For example, the cat ear is over there in the corner. What is it? So I want to extract important information from there and bring it here. And then if I want to continue this in whole image, at the end also I have this one that I replace. What I am doing from whole image, I'm kind of abstracting. I'm kind of taking important information to next level so that I can use them. It is clear that my size is reduced and I'm trying to bring critical information. Now the question is, okay, how can I bring those important information? How it's possible? How can I say what is the important here to bring it here? The answer is simple. First of all, we say that we calculate the weighted inputs, then we apply some filters that we will introduce soon. So we say we can use different filters to weight the extracted local features, and features need to be shared parameters to cover important complexities in the data. For example, let's say I can define one filter that in that window that I showed you, I want to apply, for example, this filter that is the diagonal filter, and it says that, so I want to detect the lines like this from the image if I have image problem. So you can see filter is 1, 1, 1. All of other values are negative. It's a matrix. I apply this filter on that image. I want to detect these lines. Actually, we will see exactly also how it's happening. So again, another diagonal. If I want to apply another diagonal in this direction, then 1, 1, 1. All of them negative. So if I replace it with a sliding window, in the image I'm trying to detect these lines. What about multiply shape? I can apply this multiply shape to detect all these multiply shapes in the image that I have. All the connections like that. Some filter like sum. Some filter that detects edges for me. Not only these ones, detects edge. Some filter, so this is identity filter, nothing happens, exactly moves whatever is it to the next layer. We can have blurring, so the filter that blurs my image, 1/9 times all 1. We can have sharpen, so this filter applies sharpness on my image, that you can see like all these corner values are 0, middle is some value like 5. If you increase it, the sharpness will be increased. Now let's see, like also we can have ridge detection. Now let's see each one of filters an example. I ran a code for you on this slide to make it more clear. I gave random picture, this image, as input, and I want to apply the filters one by one that we introduced to you based on the sliding window to see what is the output. Let's see. Also note that I apply on the grayscale. So let's apply this filter on that image to see what's happening. I want to detect all these lines. What will be the output? Output will look like this. So after finishing, I also will show the implementation, how this can happen. Exactly, I implemented this matrix. I slide it on the window, and the features extracted of this line will look like this. Then if I apply that one, almost same, because I'm detecting the same almost feature, diagonal lines. Right to left, left to right. If I detect multiply, this is quite different now. Because I'm detecting two together, you can see it's more clear image. But here, maybe it's hard to understand, even you don't know, you don't see the differences. But the combination together looks like this. This helps you very good understanding of what is happening. Now you see, look, this is humanoid robot, right? There are many features that I don't need, right? Like the written things over here, or these figures over here. You can see that applying one filter removes those for me, and my dimension is smaller, so that in my problem, I'm kind of removing the features that I don't need. This is called high-level feature extraction. Let's apply more. Same image. I think this filter, I replaced it wrong. I'm not sure which one was it. I should double check it. I think this is not the filter. In the slides I should correct it. But another filter, I think it's the third filter from here. Let me see. What was the third filter together? I think this is the sum here. Supposed to be sum. This is sum, then edge. So I don't know, can you see it from there? But with the edges are very clear that these are humanoid robot edges, like also extracted over there. Since just edge with some value, you can increase, decrease value to see what's the difference. And identity, you can see same image move to the output. Move with blurring, you can see this is much more blue. Sharpen, much more sharp. If you even look at the differences, it's a little bit clear over here. Then rigid detection, that detects the kind of almost the edges. So now we have understanding of, okay, feature extraction. From high level, low level feature extraction. And now I want to see how can I also use this in order to train some network to predict something as well. Before that, let's see the mathematical calculation. Now, let's say this is the part of image, the same image. I have some values over here for simplicity 1 and -1. And if I apply one window over here, so how the calculation is happening mathematically. So in convolution, so this is the window randomly. For example, we are here. This is the values over there. I just written there. Then this is the filter of sum. So some filter can be replaced here. Then the element-wise multiplication is equal to this matrix over here. Just I multiply the filter with that window. Then I write the result over here. Then based on this result that I have, I get the sum of all. Then if I get the sum of all, it becomes -7. So applying the convolution layer for that sliding window for this part gives me value 7. And if you see, if I do it in whole, I will be smaller. Output looking like those values. Clear? Let's see over here what is happening in whole image. For example, if you have 5 times 5 image, and this is the sliding window, I want to slide in whole image. So we want to apply 3 times 3 filter. This is the filter, the sum. What is happening? So this times over there, the values that I can get, and from those values, I get the sum and put the value here. If you look, we have only 2 ones, 2. So the note is, the image was 5 times 5, the output, new frame looks like 3 times 3. So I'm shrinking the size also at the same time that I'm applying one filter. So if we continue this, now with the sliding window, we can have different strides. Stride means that how many steps I want to move this window to the right and to the next step. So there are a couple of points here. So can I increase this stride not only 1 to 2, 3, 5? Yes, you can. The first point, there is no limitation for that. But basically, we want to have some overlap. We prefer to have some overlap. If you have bigger stride, the size will be smaller over there because you get less value. But the point is, when you're doing this stride, then maybe this jump out, right? Maybe this window, if you move it 3 times, comes here, then you don't have anything over here. Then what you should do, there is a technique called padding. You need to add some fake values here that are not affecting the output, but you make the image bigger so that your filter can be used with that stride to move in all image. So you need to calculate it. If by the values that you're giving, the filter size, and the stride that you're giving, you want to move it, you should make sure that image size is fit enough. If it's not fit enough, in the code you will see, you can add padding, then you will add fake size, make the image bigger so that it can move. Clear? Now here in this example, just we have stride 1 and the filter 3 times 3, no problem with that. Let's see what is happening. So from beginning we came, it was here, we calculated value over there. Now we move it to the right, apply the same filter and get the value. So this times this becomes this, sum of all becomes this, very simply. We move it to the right, stride 1 again, then again this times this, that, and the sum. We move it next step. Look, because stride is 1, comes down 1. If it was 2, would come 2 times. Then again calculate it 4, 5, calculate it 4 again. I'm continuing, calculated 3, calculated 5, calculated 4. Now, what does it mean? It means that the features that I have from this image abstracted or lower level features are extracted over here. Maybe this part is more important. You see that there are more ones here, right? In the right down corner, there are more ones here. The value is bigger here. Maybe it's darker, maybe there is something in the image over there. So the values of the right side, right down side is bigger. Here is smaller. So if we want to define the sliding window in simple understanding and the math, we say that in convolutional neural network we have matrix or weights of the Wij because we have inputs and the weights that we are going to find for network. We moving a sliding window on the input data, and we get linear combination of them, and we apply later on we can apply nonlinear activation based on the need on those two. So we have convolution layer now, then we can use the same nonlinear activation that we studied for neural network over here too. So if you have 5 times 5 filter over there, we have this output that the equation formally looks like this. I told you I'm talking about pixels for simplicity, but what is happening in fact is the weighted input that added by some bias. Sum of all of them causes all this comes into 1. If you want to implement all this explanation, again we have very simple task, 1 line. We write convolution like self.convolution1. This self comes from the class, nothing too much important. Convolution 1, the layer, I will show you the implementation, equal to neural network, the library, dot convolution 2D, two-dimensional convolution, and all the parameters that I have. What are the parameters? Input channel size. This is channel size. Don't mix it with the size of the image or something. So if you have grayscale, we have 1 image. If you have RGB, we have 3 over here. So first value is the dimension that we have. Second value is what? Number of filters that I want to apply on my input. What is the number of filters? The filters that we studied. I showed you some examples. So for example, here I want to apply 6 filters. You may say, okay, which one are the filters? Library already implemented for you. You don't need to define it. You can do, but you don't need to define it here. You just say, my input dimension is 1. I want to apply 6 filters. I want to apply 16 filters. I want to apply 25 filters on my image. So that, what does it mean? It means that, so if I apply 1 filter, I slide it, then I will have some output for filter 1. For filter 2, again, I apply filter on whole image, I have second layers of that output. So that it should be also clearly understandable for you. So we have layers of the output because each filter is slide in the whole image. It's right, I explain what is the step that I want to move this filter. And padding is here 0. It means that how much I want to add padding if your input size, image input size, and it's right, and the filter size is kind of that you need padding, you need to add it. If you don't need it, let it 0. Why here? Because if I add step 5, like comes 5, then comes 5 goes out of the image. Then I need to add padding over there that my sliding will work. Clear for everybody? This line of code is must. You must understand clearly. Yeah? What? 6 is number of filters that we have. Number of filters, kernels or filters. So filters also called kernels. Whenever you hear kernel, filter is the same. Number of that positive divide or whatever that I showed you, number of these. Again, I show you. Let me go back. Here. For example, this one. Sharpen, rigid detection, number of these. Now, what does it mean? It means that I have image. If I give it to this convolutional layer, what I'm expecting that my image as input is grayscale. I will get 6 layers of output that is smaller because gets smaller based on this stride and pattern. Now you may say, okay, what is the use of that? How can we use it? We had image, now we created many more images actually. From 1 image, now we have 6 images. It's smaller, but what we should do with it? Let's see. So, if we have RGB, we have 3 channels. With these 3 channels, of course, we have the image size, X and Y, and we have the Z. That Z can be shown the depth. If grayscale, just 1. If RGB, 3. Now, I'm applying this. Let's say I'm applying the filter with different stripe. So when we are applying the filter, the same filter on RGB image will be applied on 3 of channels. So per each channel, I will apply the convolution layer, the filter on it, and I will get, like this part, I will get the small part. And if I continue that, I will get, of course, as I explained, a smaller image based on this scale. And if you continue that based on different filters, you will see that per each, I didn't draw it over here, we have per each channel also a couple of more, per each colors couple of more, same, and much more layers, and the D is increased. So X and Y was the dimension of input. W and H is dimension that now newly I have. Usually is smaller, but more layers. As I said, we want to see now how we can use it. We will discuss it soon. The question is, the problem is, the size is increasing, right? although the size of one frame of image is shrinking, getting smaller, but the whole input data size is increasing actually, right? I've written maybe over here. First of all, you should answer why maybe. Maybe is increasing. Hugo, you can answer also. So it's clear, I have RGB image, 3 channels. When I apply convolutions, this is increasing the size, right? Maybe it's increasing. Why? Maybe? That's one. And second, we should do something else too. Just use one filter, for example. Not use too many filters. Yeah. So I want to make sure everybody understands what is happening. So if you use one filter and it's right and the sizing and padding everything somehow, that is not increasing. It is possible. But basically, we want to increase it. We want to apply a couple of different filters. When we are training our model, we don't want to use one filter. If you use one filter, you extracted one kind of feature from your image that usually output is not detectable. We usually use 16, 32 different filters minimum. So that from different perspectives, you want to evaluate your data. So that each one separately can come to the next layer and gives you some information that we want to use it later. Okay? Now, when we're doing that, so we say that, okay, we need it. We need to increase the dimension. We need to extract more information, apply 32 filters. And my information is exploding in one layer of convolution, like the information comes 10 times, 20 times, maybe 100 times much more. And now usually we don't have one convolutional layer. We add second convolutional layer, then multiply it again. Then that grows exponentially and we cannot stop it. There is a solution to do that. The solution is that we can use the pooling layer, that when you are doing input comes, you're applying those filters and layers and your data grows, you want to shrink it back again, then add second layer of the convolution. That's called pooling. With the pooling, what we do, the idea is similar to filter, but the objective is make the data smaller. One of the common pooling techniques is max pooling. That let's see, if you have this image, whatever the values is, and let's say like it can be the output of first convolutional layer, or for simplicity purely image. What we can do with max pooling, we can say that, okay, let's say in this area, what is the important information, but not like filter. What is the important information by getting maximum of the value over there? Simply. So for example, if we talk about black point over here, and if we do like small points, so it's small areas on this image, you see that like there is not much information. If I put the maximum of each pixel over here, like by getting this, you can see that almost the image is remaining the same. If I apply it again, you can see that almost image looks like a human. We are not losing too much information, and shows that this is hair, this is face, this is body. So what we do, this part, getting the max 3. Then another part, this part, getting the max value 3. So we say most likely the most important value, what is it? I'm replacing over there. This part over here, that part over here, so that we are doing downsampling. The values are, I think I should fix them. Also, I changed the slides a little bit. I need to fix them. Those are the maximum values, should be 3, 3, 3, 2 here, 5, 1. So how we can implement it? Neural network, the max pooling. two-dimensional. We can define the kernel size, and we can define the stride over here. So with the neural network max pooling, how big the size of the kernel that I want to have. For example, in this case, example is 3. Stride 2 can be 2. If I want to write it exactly for this case, I can write 3, and step is 3. These should be for this figure. I can write stride 3, and the kernel size 3. Any question so far? So imagine to understand what happened so far. Imagine that we had the input. We applied convolution layer. With some filters, data get bigger, more dimension. Now I want to make them smaller by applying some max pooling layer to that. And that layer can be defined again by one line. Now if we want to have a look at all steps together, we have the image. We apply filters. By applying the filters, by number of filters, if I have 3 filters simply here, I have 3 layers on one, for example, grayscale, that the dimension maybe is smaller. Then if I continue that, so since the one image get 3 times bigger, I want to make it smaller. I apply max pooling. With max pooling, I say that important information can get smaller. When to use it, you may say, if we don't use it, is it okay? Yes, it is okay, depending on problem that you have. Can we use it should we use it after, if we have multiple layers, can we use it, or should we use it in all layers? No, maybe you use it in only one layer. Maybe you don't use it, up to you. That's the configuration of network that you want to do, depending on filter sizes, number of all parameters that you adjust, and finally, the max pooling, you make decision. Now the beauty is that with all those features that the convolution layer extracted for me, these are the features, low-level features that extracted for me actually. For example, look at this image. Lots of details, low details. How should I decide that which one of these is better for me? Actually, this is output of max pooling. Don't consider that, but actually we are doing the same, like extracting the features. Maybe that's not very good example to discuss. But anyway, here we have the low feature applying the filter. For example, age. For example, the amount of important parts that we have on different filters. Each filter represents different perspectives for me, and I may apply different layers with different filters, and they mix. Finally, this represents, for example, edge for me. This represents blue part for me. This represents another part for me. So that, based on this, what can I do? Now I can say, okay, I already know that I can have fully connected neural network. And I can flatten this data and give it to my fully connected neural network and train whatever I want. Like prediction task, like regression task. Last week we saw one example we solved with the code. This can be now reacted as input. Instead of giving this directly to this layer, I could do, now I applied some convolutional layers and give that to this one now. What I'm expecting that learning from here is easier and better than learning from there. Is it better? Yes, it is better. In most cases, it is better that we have convolutional neural network and makes deep learning work better. With advanced networks, if you look at, I will show you also, with advanced structure of neural networks, you will see that we have different combination of these. Like some put two of these passes, different combination of these all together to finally get the output. How many fully connected layers here? As I said, usually one hidden layer is enough. The same rule is working here too. Usually one hidden layer is enough. Doesn't matter how complex the left side is. You should have enough fully connected layers. In some cases, we add two. not usually more than 2, but then the output you get can be probability of being in one class or something. Here we have some notes. We should add, of course, nonlinearity function here in the middle. For example, ReLU, activation function. Also, we should have, usually if we need, we can have batch normalization over here too. I said after each layer we have it. We explain it on fully collected network and neural network, but also we have it here too, doesn't matter. So same batch normalization and nonlinearity can be used on convolutional neural network. That what it was doing, normalizing the data to don't let the weights and values grow. And what is the implementation? Very simple, one line. Self.batch normalization 1, for example, in the layer that we want, I will show you in the code, neural network dot batch normalization 16. What does it mean? This means that I want to apply the batch normalization with size of 16 on the layer of input that is coming there. Couple of notes also for fully connected layers. We say if it's classification task, after all those calculations that is coming here, these values over here are not probabilities, are some values. Because we had x weights, many things. Max pooling, getting the dimension is smaller, whatever we applied, these finally come some values for me. So now I need to, if I want to use them as classification, say, okay, this is like probability of being cat, dog, bird, elephant, etc. I need to apply one more thing over here on this layer that is called soft max layer that converts everything to probability. Very simple. It's a mathematical function that converts a vector of numbers into vector of probabilities, gets this value and says, okay, what is the probability for each? And this is the equation, and this line can do that for you. So when you have classification problem, you need to apply one, for example, softmax at the end layer that says neural network softmax dimension equal to 1, so that the dimension normalized values along which axis that we want over there. Then gives you the probabilities over there. Like. This is the network that I did myself long, I don't know, maybe 6-7 years ago, 5 years ago. So you can see the image, clinical data for cancer. The image size that is coming and dimension. So 220, 160, and 3-dimension RGB. So I applied convolution, kernel size 3 times 3, stride 1, padding 1. And this is the output, what is happening. So you see that the 16 is the dimension that I didn't write here. I applied 16 filters. So I have 16s of the image, 80 times 110. Then again, I added second layer of convolution. When I added second layer of convolution again with kernel size 3 times 3, stride 2, padding 1, 32 different filters, you can see that it's grown. The image gets smaller because of the stride and the padding. Gets smaller, but the dimension, in that case, the filters are much more. Again, 64 filters with other, then gets, and again, one more. And after all the convolutions layers, my figure looks like this. Then I added 2 fully connected layers for that one to train what I wanted to do. So one example. If you look at the well-known networks like YOLO, you look only once. YOLO is an image classification problem. It's an algorithm that is very famous. What is it doing? It is finding the the location of localizing where are the objects and what are the object types at the same time. Those two tasks together. Classification problem and localization problem solved together. But we are not going to talk about that now. We just want to see that, okay, you can see that in YOLO they have convolutional layer 7 times 7 times 64 is right 2. You can see that this is happening. Convolutional layer again, convolutional layer again, convolutional layer again. The same concept that we studied. Then finally goes and ends up with the task that they define. That's the link I put for you if you are interested in to study. There are different versions of YOLO that you can see. YOLO version 1, 2, 3, 4, 5. This plot shows YOLO version 6, for example, that how good it is based on the result. So the data and the prediction of the model, and shows that why YOLO 6 works better based on the plot, the results that we have. And you can have a look at the different configuration of each layer, and you can see that they change the configuration of the convolutional layers and the fully connected layers and different layers to finally end up with what they want. Later, if you have, I'm not sure, but if we had time, we could also study. Okay, any question? Let's finish these slides. We have just few slides, then we have a break, then we see the implementation. So popular deep learning algorithms are LeNet5. You can search and see how its structure looks like. Not something very extraordinary. Combination of convolutional layers, neural network, and fully connected layers. Dan Krisen, AlexNet, Overfit, VGG, network in network, GoogleNet, and bottleneck layer are some of the most common ones that I represented here. For example, you can see the AlexNet, one of the ancient of the network that we have, very famous. If you look at the input, you can see that there are, now you can easily understand. Input comes, max pooling, the normalization, and there are two tracks of those, max pooling, then again the different convolutional layers, and finally there are dense layers. Just the innovation is here that dense layer, they connected to each other too. So two dense layers in parallel trained, and they share the weights of the networks over there too. And the idea is that this pass learns some features, this learns for some other ones, then we can merge it together at the convolution, at the end fully connected layer to predict what we want. So you may have a problem. You apply AlexNet, then you may create another path, combine, mix, to finally see that, okay, your algorithm works better. I told you there is website Kaggle. They put data set every month. There is competition with price to see if you can propose better network, have higher accuracy over there, then you can win the also competition. As I told you today, I will also show you how to solve one. Generally, popular deep learning algorithms, we saw the convolutional neural network, CNN, we have the LSTM, long short-term memory network, recurrent neural network, we have RNNs, we have generative adversarial networks, GANs, we have radial bias function networks, RBFNs, and we have multiple layer perceptrons or MLP. We saw also MLP, we saw convolutional networks. These are also other structures that we have. Plus we have self-organizing maps or SOMs, and a couple of more that these are more common ones. If we bring all together into code, you can see here, I will explain it soon, but let's have a quick look. We define the convolution layers that we want. You see convolution layer, like convolution 2D, number of input channels, number of the filters that I want to, kernels that I want to apply, the size of kernel, the stride, the padding. Then after one, I have applied, like in this example, batch normalization based on that number of filters that I have. Then second layer of convolution based on the output size of that dimension that I have, filter size, I get it, I apply number of filters that I desire. Then batch normalization on the output of that one. Could we remove it? Yeah, we could remove it. For this example, we discussed why we have it. Convolution layer 3, again 32 as output input. Again, I applied another 32 filter with kernel size 5, stride 2, padding 2. These are the same here, could be different, up to you. And again, batch normalization, and finally max pooling over here. Now you should know what's the max pooling and why we are doing. What's the batch normalization, what we are doing. Also, you can imagine the whole mass calculations over their background. After defining the layers that I want for convolutional neural network, what I've done in here, I calculated 2 lines, all this mass. The mass of the... So after you apply the convolution layer, we want to connect with fully connected layer, right? But that fully connected layer, I should know what's the size, right? How many neurons I should have. That size, I need to calculate it based on this kernel size, stride, and padding for each layer. So to do that, I usually write a function that this function includes equation, simple equation that calculates it for me. So I define the convolution to the size that gets the size, kernel size, stride, and the padding. All these inputs comes, and with some simple equation, size added by 2 times that padding, subtracted by kernel size, subtracted by 1, and whole subtracted by 1 over stride added by 1, can give me 1 layer's calculations. It means that the input, whatever I give, after applying the kernel, the filter that I have, this stride to padding 2, what will be the output size? This calculates 1 layer. Since I have 1 here, I called it 3 times. So I call it the convolution to the size, calculates, give me the size that I get here, again goes to other layer, right? This goes to the other layer, and this goes to the other layer, since I have 3 times of calculation for the convolution width. For height, again, I calculate the same 3 times by sending the size of the height of the image that I have. Then I do this, I have the fully connected layers, initial size, not the frame size that I have, then I should do a simple another calculation that say linear input size now is the multiplication of the width and height and the 32 number of the things that filters that I have over there. So this line can say me what is the size of applying all the convolutions calculations, what should be the neural network fully connected layers input size, so that I can use it to define it as here 1 line. Neural network linear input size, I calculate it, what is the size. You may say I want to write it by number, calculate myself, you can do, doesn't matter, but this is automatically. And the outputs. So the output comes as input parameter over there, the size that you want. For example, if you have classification task, you have 10 classes of 10 classes that you want to say you want to get probabilities, you send it to here. For example, if you have 10 classes, you send 10 classes. The input size of fully connected will be calculated automatically, and that's it. And of course, you need to also send parameters of the size of the image, what size of image you want, and what is the output classes that you have. So this is the definition of the convolutional network. One last thing is the forward step. As I mentioned last time, briefly, we have image, comes to network. We propagate forward and calculate the output, calculate the loss and back propagate. We said that in Torch, we don't need to implement back propagation. Automatically, it will be implemented in background. We don't need to do that. In other libraries, you may need to write it. But in Torch, we don't need it. We just need to write forward propagation. What are the details that we want? How we write it? We should define forward and the input. So definition of forward automatically will be used when we are running the code. I will explain in the example. So also you don't need to call this function. Automatically this will work. So how? Forward with the x as input. What we need to do, we say, okay, I have the x equal to f. F is coming from the library. I didn't show it here, but we'll show you in the code. Comes from the importing the library. F.relu, I want to apply activation function relu on the self dot. So bn1, what is the bn1? Batch normalization layer 1. I want to apply relu activation function on this batch normalization layer 1. So that this batch normalization layer 1 is the output of the self.convolution 1 on the x, this one. So applying convolution layer 1 that I defined over there on the x, I apply. So the x comes here input. Input goes to the convolution layer 1 that I defined here. Whatever output comes from that x's goes to batch normalization, then apply relu activation function, then come to the x. Then whatever the x is, in the second layer, I want to apply second layer of convolution, this one. Then second layer of batch normalization over there. Then again apply relu. Up to us, I may remove it. I don't want to apply relu. If I want, I apply relu on that output, then apply the pooling. Again up to me, may I remove it? May I remove this relu too? But here I wanted to have pooling, relu on the output of second layer that I defined here. For the third layer, what I did, self.convolution, I applied third layer of convolution that defined with that kernel size and everything over here. Yeah, on the x. And this x again is coming, right? Coming as first layer, second layer, third layer. Whatever output is, I apply, then apply relu on it, then apply pooling layer on it, then I have the x. Now let's see what is the size of the x and the shape of the x. I can print it. Print the x.shape. I will see after applying all these calculations what will be the shape, the size that I have. And lastly, what we have here, the self.head, x.view, x.size. What does it do? This is just resizing the reshaping the size to one dimension so that I can use it. This is whole implementation of deep network. In for example, reinforcement learning, you can use it. In prediction tasks, you can use it. In classification tasks, you can use it. You can combine whatever you want, change the parameters, combine whatever you want, change the parameters, and train the model. So for training model, I will show you in practice this code. Now you can have rest if you don't have question. Then after 10 minutes, we will move forward to implementation. Clear? No question? Okay, good.